Gone in here. Hello. I want to get started so my partner doesn't go Johnny 5 on you guys, because he will. He's got a lot to talk about. So, everybody, welcome to Shell Shocking for Fun and Profit. Too early, too soon? All right. Just kidding. So how many of you guys have ever had your credentials show up in a part of a public breach? You're all lying. I see like 2 hands. It's okay. I mean, you're not bad at what you do because somebody else messed up. All right. All right. So wouldn't it be awesome if like that never happened again? That'd be pretty cool. Can I get like some? Wouldn't it be awesome if it never happened again? All right. Good deal. All right. So Ben and I are here to discuss something today that he's been working on that we feel like is going to make this a reality or a real possibility moving forward.
Cool, yeah. So real quick, I just wanted to give a couple shout outs, some thank yous to everybody who's helped me out along the way in developing this idea, working through this and in testing everything, and just in all around moral support as well. So yeah, thanks you guys. I'm Benjamin Donnelly. You can find me on Twitter and around the internet as this very weird name, Zax. I'm a security researcher / pen tester. Please no beer. I'm not old enough yet. I do accept protein shakes. So yeah, you can find me. You can find me on Bitbucket. You can find me on Twitter. You can find me in your deepest, darkest dreams. All right.
And for those of you who don't know me, I'm Tim Tomes, also known as Landmaster 53 in some circles. Pretty much all you need to know about me is I do all this stuff in the middle, trying to achieve this bottom bullet, and all while doing that, glorifying the guy up in the top left-hand corner there. And quick shout out to my brothers at Hackformers and Proverbs Hackers. So, quick rundown of what we're going to do today. I'm going to talk a little bit about the problem in our current status of stored credential security. Then I'm going to pass it on over to Ben, and he's going to chat about his philosophy of moving forward and talk about his solution in ball and chain, and then we'll wrap it all up at the end in what I call the future, okay? So first of all, what's the problem? Well, the problem is that all of our current implementations for stored password security are horribly broken, okay? If you want some backstory in that, I did a talk at B-Sides Augusta a couple weeks ago called Stored Password Security, where I go into great depth on all of our current implementations. But to make a long story short, if we're storing our passwords in plain text form or encoding form, right, we're one SQL injection away from having all of our users' credentials dumped to the public. With encryption, we're not doing a whole lot better. Right? Encryption requires a key, right, some sort of key in order to create the ciphertext, and that key has to be stored somewhere where it's accessible to the actual system that's doing the decryption, that's doing the authentication. And so really, if we get one step beyond that read-only SQL injection, there's a distinct possibility we can gain access to that key, and then everything becomes plain text again. All right? Fast hashing is exactly that. It's fast. It's designed to be fast, and anything that's designed to be faster is actually going to help someone trying to calculate it or compute it. So the crackers actually benefit from us using fast hashing algorithms to try to protect our passwords. Okay? And on top of that, users create pretty weak passwords as it is, so that just makes the situation even worse. Okay? And then we have adaptive hashing, or slow hashing. Now this is harder. It's harder than fast hashing, but the overarching problem with all of these is every single one of them is vulnerable to an offline attack. And this puts us into a computational war with our adversary. Okay, so our current approach to stored password security is a lot like a seesaw, right? Now on one side of the seesaw we have the strength of our algorithm. And then on the other side of the seesaw, we have the strength of our password. Now, in the instance of fast hashing algorithms, they're pretty weak, right? They're designed to be fast. So our passwords, our users' passwords have to be pretty strong in order to make that a relatively secure system. Well, our users don't want to create strong passwords. They want weaker passwords, or they're going to make them anyway if we give them the ability to do so. So we try to use stronger, slower calculating hashes in order to allow our users to use weaker passwords. And we begin to make this really, really bad assumption that because this is harder, our users can create weaker passwords and we win. But the problem with this is that our adaptive hashing functions, they get their strength by how long they take to compute or how difficult they are to compute, right? And as far as computational difficulty goes, our adversary or the attacker is always going to have the advantage. So why is the attacker going to have the advantage? Well, mostly because their focus is different than ours is, okay? We implement these systems because we're trying to authenticate. We have a system or a service that we need to support with authentication. But with that authentication comes a whole lot of other things, right? We have a service, a company, a business process that we're trying to support with this, so we're worried then a heck of a lot more than just encrypting our hashes or encrypting our users' credentials, okay? Harder computations for us, well, they result in a greater cost, whether that be uptime, resources, funds, whatever it is. Higher computation will result in a higher cost. But let's look at the attacker. The attacker probably has one objective, and their objective is to what? To crack our hashes, right? Well, and they don't even have to crack them all. In some cases, they only have to crack one to get the information that they're after or to get the access that they're after. And when it comes down to cracking that one hash or that group of hashes, well, they can distribute it. They can distribute it amongst a botnet, or they can distribute it amongst a group of people that are willing to help them achieve this goal. And they can also build powerful machines that are intended to do only that, crack our specific hash. Okay? So that being said, they have the computational advantage no matter what we do because their focus is completely different. So what do we need to do? Well, we need to make better and more secure assumptions about these systems that we create. And we ought to start by looking at the worst case scenario, making assumptions that our attacker is a dedicated nation state ready to attack only our hashes. Okay, now that may not be true, the true threat for everyone, but we need to start with that as our baseline and move forward. We need to assume that we've got limited resources that may result in both our hashes and our users' passwords being weak, which essentially breaks that seesaw model, right, in a horrible way. Okay? So this paints a terrifying picture in terms of how we move forward and how we build these and build up from this terrifying picture in order to create secure systems. But in addition to these assumptions, we have the grim reality. Okay? And then some of these realities are the business, our business, they don't want us to spend more money so that we can do things slower, right? I mean, if you go to your boss and you say, hey, I want to buy this equipment or I want to implement this algorithm, which is awesome, it makes everything slower and it makes our stuff work harder, what's he going to say? Unless you do a really good job of conveying that risk to him, in a lot of cases, they're just not going to want to move in that direction. The other thing is our users have been loud and clear in the fact that they don't want to create strong passwords. They don't want 25-character alphanumeric special passphrase type passwords. They want something that's easy for them to remember and easy for them to type in, right, quickly so they can get to what they want to do. Right? And us, we don't want to enter into a computational warfare with the adversary. Right? So in order to make some advancements in this battlefield, right, to win this war, we've got to do a couple of things. First thing we need to do is identify and exploit advantages of the defensive position or the defensive perspective. That's step number one. And then step number two, keep in mind the restrictions such as making passwords easier to remember for our users. And then I think there's a third thing involved here, and that's getting people that are smart enough to figure out number one while considering number two to help us implement these systems. And so with that, I'm going to bring on Ben to come up here and talk about ball and chain.
All right, guys. So real quick, I'd just like to really quick put one or two slides in here on the philosophy of why I did this. I'm 20 years old. It's a little bit weird that I spent a good year of my life trying to research how to fix broken password security. And I think it's important to talk about it just simply because I really want to see everybody in this room doing it. I would really, really, really like to see that, right? The internet is kind of broken. Not entirely. There are many portions of it that are completely decently secure, right? But the internet, it runs through all of our lives. And it's only going to become worse and worse and worse as time goes on. We need to check ourselves. At this point, we need to be trying to build things to be as secure as possible, right? We're fighting a war here, and one that we really can't afford to lose. I heard a really, really, really great quote once that basically said, without empathy, we're just solving puzzles. If you guys go away with nothing else, if you guys don't like my algorithm or anything like that, I would like to see you guys go away thinking about that. Don't just solve puzzles. Solve problems. Find things that are actually a problem and spend your time trying to solve those. You don't have to try and be clever. It's not always about trying to be clever. Sometimes it's about being willing to fail for the opportunity to potentially do a great thing that could really help some people. So, secure by default. That's the philosophy that I undertook when I went out to try and design this system. We know that users don't like to use strong passwords, right? But it's also very, very hard for us in terms of visibility to see into a network, to see as a computer sees. right? To really respond in real time, we need sophisticated, advanced, interesting tools. I want to see you guys building systems that are secure by default, things that are just inherently secure. We want to make our users' lives easier and not harder. And we need to stop relying on our users for our security. So my hope here is to make passwords fun again. If we can make it so that you can have passwords that are short, concise, easy to use, if we can stop offline and online attacks, then maybe, just maybe, passwords can stop being this evil thing enforced by the higher echelons, right, with these ridiculous password policies. So let's talk about it. Oh yes. For example, secure by default. You want to stop bugs from flying through your window? What we do nowadays in security is we generally try to sit there and try to catch the bugs, right? Literally. Try to catch them. Let's just put a screen in our window. That's common sense to anybody, right? So here's the solution that I came up with. A potential solution, and I'm really, really hoping that if there are holes in it, if there's something wrong with it, I want you guys to be the ones to come to me, tell me how I screwed up. Let's try and make it better. Let's try and make this work, all right? Ball and chain. So the defensive advantage does, in fact, exist. I thought of one. You know, we own the data at rest. We also own the surrounding infrastructure. I mean, assuming you are the defender, you own these things, right? The attacker has to come into our network, and he has to steal our data, right? Through our infrastructure. Now, that's pretty easy, right? Downloading little bits of data, that's not really a problem for any sort of dedicated, intelligent attacker. In fact, it's going to be very, very hard for us to stop him from doing that, right? Exfiltration is pretty simple. It's not the easiest thing in the world, especially if we're trying real hard, but it's pretty simple. What about downloading a ton of data, like terabytes and terabytes of data out of your network? That might be a little bit harder for him, right? I mean, if we assume we've got a limited sized pipe on the way out, that's going to be pretty difficult. And especially what if we were like monitoring for large downloads, monitoring for any gigantic things going clunk on the network, right? And to note, you don't have to do that, but it could help. So here's an example. Here's the logical overview of the idea that I came up with. Say we create a huge file on the network, a gigantic file, a monstrous file, a titanic file, okay? Then we're going to tie user authentication to that file, all right? So to check if a password is valid or invalid, you'll need the password hash. It's not a hash anymore, but the password representation format. And you will also need this huge file, right? So even if the attacker goes into your machine and he dumps the database or something and he gets the stored hashes, he's still going to need this huge file in order to be able to, to crack the hashes or even to make a single guess against the hashes. Have you ever tried downloading a multi-terabyte array? I've tried to download some multi-terabyte rainbow tables once or twice, and it's not terribly fun, and it doesn't work out, and it takes an eternity, and you end up just like kind of buying them from the manufacturer or creating them yourself, right? The attacker's not going to download it, not if we make it sufficiently large. In fact, he's never going to download even a significant portion of it. The sky's the limit here. We can make this thing as big as we want. So if that's true, then the attacker cannot perform an offline attack, right, based on the logic on the previous slide. So I put a simple little graphical example here. It's pretty bad, but there's your network, right? You guys see your network, and you see my little hashes over there, and you see that big old fat file, and then we got a tiny little data pipeline. This is like that game when you're a kid with like the smash the shapes with a hammer, right? The hashes can fit through to the attacker's network. Woo! That big old fat file is not going anywhere. That fat file is not going to fit through that hole. Got it? Cool. For example, my home upload speed is 6.14 megabits per second, okay? According to Wolfram Alpha, if an attacker attempted to download a 2 terabyte array from my network, it would take him around 30 days just to download that array. Keep in mind, I could make the array bigger. Keep in mind, this is him using the entire pipe. I would notice this pretty fast, right? This would be super easy to detect and just be like, get off my network, no, right? If he somehow managed to get it off my network by being super sneaky, taking like a couple years or something, I don't know. He has to do all of that before he can even start attempting to crack the passwords. This is basically infeasible. So the beauty of it, it's secure with minimal human interaction, right? We don't need strong user passwords because the attacker can't even make guesses against them. I mean, yes, they need to be decently strong, but they don't need to be anything like what we've been pushing towards lately, right? Also, it basically protects itself. You don't have to sit there and monitor and try and determine all the time. I mean, if it's a 30-day download and assuming there was no other ways to get it, check every 15 days or something, right? This thing is so big, it basically protects itself. So if this logic is true, and if it works, right, you could assume, therefore, that perhaps offline password attacks could go extinct. That's pretty cool, especially considering it's cheap to implement, and I got a quick slide on how it scales with your business. Small startup, 6 megabits per second, 2 terabytes, maybe on the order of $100. Maybe you're a slightly larger business, a medium-sized business. You get a 15 megabit per second upload, right? So maybe about 5 terabytes. It's about the same time, right? On the order of $250. Pretty cool. So here's why we call it ball and chain. Just thinking about this huge file right now. It's like a huge fat weight tying down the attacker. Now, it's a beautiful picture for all you blue team guys, isn't it? Right? Because he has to extract it from the network, which, as we already talked about, is a huge proposition, right? Distributing it, that's going to be a pain. If he wants to hand it out to all his buddies, right, he can't just post this thing on Pastebin and be like, hey guys, crack these hashes for me. Oh wait, also, here's a 6 terabyte array, just to download this real quick. Get back to me in a couple months, right? Loading it up to a cloud cracking service, that's pretty much out too, you know? You want to buy like a bunch of terabytes on AWS? Anybody? And spend time uploading it, right? Hosting it for others. So if he's all clever, he's like, all right, so I can't upload it anywhere, but I can host it on my network and let you guys have access to whatever parts of it you want. Right? Well, that's going to net bandwidth issues. That's probably the best way to attack this right now, right? If he somehow manages to get it. That's the best way to distribute it. But it nets bandwidth issues, right? So he's going to have to sit there and upload. His pipe has to be very, very wide if people want to try and crack it quickly, is what I'm saying, right? It's loud, it's clunky, it's easy to track, it slows them down good. So let's talk a little bit of a technical implementation or how this might actually be possible, all right? Our shopping list. You're going to need a cryptographically secure pseudorandom number generator. If you want, you can also get a source for true random for creating the array. That's up to you, right? We're going to need a block cipher. And I know, I used counter mode. Oh God, I used counter mode. So technically we were kind of using a stream cipher, but don't worry about it. That's because of padding oracles. So I chose AES 128 in counter mode for the proof of concept code that I'll be releasing after this talk. Whatever works. All right, guys? A hashing algorithm. You are going to need a hashing algorithm. It can be something like SHA-3. It's got to be secure, but it doesn't have to be slow or anything like that. We're not reducing this problem to a previously solved problem. Then you are going to need a data storage mechanism like a multi-terabyte network accessible storage device. That's the only thing that should cost you money, unless for some odd reason you feel inclined to pay for any of these open source algorithms listed above. That's on you. So here's our trick. If AES 128 in counter mode decrypts with an invalid key, it should give you some sort of random gibberish BS output, right? You're just like, what is that? Get it away from me. That's not my message. And usually you look at a message and you encrypt something, right? You encrypt something and it's like plain text and you decrypt it again. And there's an order to it. There's a human order to it. You can tell. What if we created a plain text that looked exactly like a failed decryption? Like, exactly like. What if our plain text was total random gibberish and it was impossible to tell the difference between an invalid and a valid key? Okay. Let's build a gigantic array, a gigantic file of entirely random data, either pseudo or real, right? We'll pull some data from that array at some specific location. We'll store that data as our message. Okay, so anything that goes into our block cipher is going to need to be 100% random. We're going to delimit everything by length because we can't just put like commas in or anything, right? It's got to be 100% random, and we will be having multiple fields. And it has to be deterministically confirmable as ours. We have to be able to go back and say, okay, here's a completely random looking message. Now let's go back and determine whether or not that's what we actually meant to send, right? So we're going to talk about how to create the array real quick. It's super easy. We talk about how to store a password, perform authentication, and then I'll go over a couple specifics and shortfalls as long as we have time. I wanted to throw a couple of the more advanced things in there to try and give you guys good stuff to think about if you're interested in this idea. And I will be releasing a white paper shortly as soon as I get that all polished up that should cover every single specific and shortfall that I have been able to find, and help me find more, please. So creating the array. Pick a decent size. Talk a little bit more about this at the end. You can use either true random, right, as I said before, or you can use that cryptographically secure pseudorandom number generator. What I want you guys to do is please, if you develop something like this from this template, if you develop something like this, please do not use a pseudorandom number generator and then like put the seed like right at the top of the array. Like, here's the seed I used to create this. Because the attacker would be able to just take the seed and walk away and go build the thing at home, right? So, yeah. All right. Let's store a password. We've got a huge array of magic random data. Cool. Let's say this is a portion of our array. This is a small portion of it, right? Because it should be way larger than this. Let's select a few pointer data pairs. So we're going to select some sort of pointer to the array, such as row 5, column 4. Okay? That'll be our pointer. Then we'll also pull out the data at that location. Okay? Cool? We're going to do that a couple of times. For the slides, I do it 4 times. In practice, I've been doing it 10 times. We'll figure out what works, guys, right? That's what we do. So let's say we do it 4 times. We're going to get 4 pairs of pointers and data. So pointer 0, data 0, pointer 1, data 1, etc. Okay? We're going to split them up by type and then concatenate the pointers and the data together separately. So you can see I have all the pointers concatenated, I have all the data concatenated, right? Okay, hash the concatenated data. This is where you're going to go ahead and you're going to use something like SHA-3. For the proof of concept code, I'm currently using MD5 because in the end, if the attacker tries to brute force our hash over here, collisions end up working out in our favor. With doing 10 times, like the entropy is like 2 to the 1280th or something ridiculous the way that I'm doing it. So he's going to get collisions well before he finds our legitimate one, which means, it can be a fast hashing function. That's totally cool. Just got to be secure, right? So concatenate the pointers and the hash of all the data. So now we have all our pointers smashed together, playing sardines, throw our data right on the side, right? This is just a quick note. It's got to be in binary format, okay? You're going to decrypt across the whole character space. So you're going to have the decryption will be random across binary, not just like the ASCII numbers or anything like that. So you got to make sure you properly transmute your data over to binary. Don't just take like your hex don't take the hex digest of your SHA-3 and like convert it from like ASCII to binary. That's not going to work. Like, you guys got to make sure it's correctly encoded as binary, okay? Here's how we would encrypt with a user's password, right? Because I haven't brought the user's password in yet. We're going to take the user's password. We're going to hash it up or in some way pad it so that it fits inside of our block cipher. In this case, I use SHA-3, which means I'll have to truncate a little bit of data off the end, right? But that works. That's fine for the example. We're going to take a random nonce because I'm working in counter mode. And if you guys don't know, counter mode needs a nonce. It needs that initialization vector, right, to kick off encryption. So that's cool. The nonce basically functions like a salt. So just think of it like a salt. We'll store it like a salt. We'll treat it like a salt. It's all good, right? Take all that data we created previously that's currently in binary form. Perform this operation, okay? User's password is the key. You got your nonce. You're encrypting the data. Cool? Bam. You're going to get something that looks like that, probably longer. A password representation, okay? Looks kind of like a hash to me. I don't see how this is so different, Ben. Cool. You can store it in shadow format. No big deal. The username is still the same. The nonce goes where the salt goes. The ciphertext goes where the hash used to go. Let's look at authentication, right? Attempt to decrypt the stored data. So this is, we're authenticating now. The users come in. They've typed their password in. We're going to kind of perform this operation in reverse, right? We're going to go in. We're going to SHA up the user's password. We're going to take the nonce right out of the shadow file or whatever we're using, right? Put that stuff in. Take the password representation. We're going to decrypt it. We'll get a bunch of random looking data, right? That's the whole point of this. We got to make sure that it's random looking data, that we can't just look at this data and say, yes, that makes sense, right? So then we're going to go out and we're going to confirm or deny whether that is the data that we encrypted previously or not. So split the data back up. Remember I said it would be delimited by length? split the data back up based on length, okay? You should have global variables that allow you to do this. By referencing them, you'll probably store them somewhere in the array. I should point out, this is a template. So I don't actually have like, a spec or anything to give you guys. So that's why I'm being kind of open-ended about you should probably have these variables, right? Some of them you can derive, but anyway. Pull it back out, you're gonna get all those pointers again. Pointer 0, pointer 1, pointer 2, pointer 3, and we're gonna get that SHA again, right? Cool. So now we're gonna rebuild all those pointer data pairs that we had previously way back on that slide back there. Take each pointer, go to where that pointer points inside of the array, and pull the data out from that location, okay? Rebuild all those pairs, okay? So this is the step where you need the array. This is the step that the attacker fails to do. This is where the attacker is going to be like, I don't have the array, and start crying, right? Once you have all the data, you can throw out the pointers. You don't need those anymore. Then concatenate the data back together, just as we did before, all right? Guess what we're going to do next? We're going to hash the data. You guys are so smart. Thank you for guessing that. We're going to hash the data. I'm using SHA-3 again, okay? Hash it. Get the hash of all our new data points, okay? And then all we're going to say is, does this hash right here match up with the hash that I had previously? Does this hash that I've just created using these pointer data pairs, right? Everything that I've just created, does this match what I decrypted when I typed in the user's key? Does that make sense? Right? So if they match, then it is incredibly highly probably, most definitely, the correct key was used to decrypt that ciphertext. Okay? If they do not match, then it is astronomically likely that the wrong key was used, right? So just to go over that one more time. If a valid key gives you 100% random output, just like an invalid key does, then the attacker is going to need the array to confirm or deny whether that was the proper output, right? Without the array, he is simply out of luck. So let's talk some specifics real quick. I want to just give you guys a hint of some of the other little bits of stuff that goes in here. Selecting a data length, okay? So I talked about how you should have a global variable set for the length of data. Well, I didn't really talk about it. I quickly was like, oh, you should have all these things. Select a data length. I've been using 128 bits, right? That's a fair amount of entropy. So the data length is the amount of data that's going to be pulled from each and every location where you have an array, or I'm sorry, where you have a pointer. So you have a pointer, it points there. You go there. This is my magical invisible array. It points there. You go there. You pull out 128 bits of data, right? You're going to do that for every single pointer. You just want it to be long enough that you don't create a chance for collisions where somebody can type in a different key and get something that works, right? So, cool. And if we're using multiple pointers, that's going to stack incredibly, incredibly fast. So really, you probably don't even need 128 bits as long as you're using enough pointers, but it also doesn't hurt to have it because it all just gets hashed together, and it's just wonderful and beautiful, and it's amazing. So when building your array, you're just going to decide on a size for your array. Make sure that the array is decently large, right? We talked about making sure that the attacker cannot steal even a significant portion of it, right? You want to make sure that he can't even get like 1/10 of it. But well, it's okay, I guess, if he gets 1/10 of it, right? Because we've used all those extra pointers. And I'll kind of explain a little bit more about that, I believe. But anyway, make it big enough. Make it a big array. Some pointer considerations have to be made. So depending on the format that you choose for your pointer, you can come up to a situation where the attacker can look at the pointer and say the pointer that he gets when he decrypts the ciphertext using some random key, his guess for your password, right? You can create a situation where he can look at that and say, I know that this is not the password. So here's how that works real quick. Obviously, it would be in binary, but I'm going to use a decimal example for the pointer. So if you had 4 indexes to your array in the format 0, 1, 2, and 3, since the decryptions from the AES, the block cipher, would take the whole character space of that, you would get decryptions that were a 4, a 5, a 6, a 7, an 8, and a 9, right? You would also get 0, 1, 2, and 3s, but you would get all these other decryptions too. So it's still infeasible. We'll assume this array is tiny. It only has 4 indexes to the array, right? But we'll assume that for the attacker, it's infeasible for him to steal the entire array. But it would be really easy to go in, maybe get some visibility to the network and figure out what the what the size of the array was, right? He could probably, that's way easier to steal than the entire array. So with that, he can figure out what some of the password isn't, right? He does this by making guesses, and since he gets random decryptions for every guess, and since the pointers are inside the ciphertext, sometimes they will decrypt to something, they'll decrypt to like a 5, or they'll decrypt to, something else, and he'll be all like, well, I know that that's not in the array, so therefore this isn't the password, which is gaining some information about your network. So here's some solutions to that, pretty quick. Just ignore it if you want. Especially if the difference is minimal, no big deal. He's never going to figure out the password, right? You can match your pointer space and the array size, which limits the possible sizes of array that you can have, right? You can use non-sequential indexes, do something like a mapping. So that way you can have like all the sequential indexes will be over here in a big old file. And then you'll put a bunch of like random ones in for each and every one, and then you just do that little like draw lines game. Like this one matches with this one, right? You can do that. Could get out of control if you really want to try and store that, and I reduce that to a previously solved problem. I say just make it too large for him to steal yet again. Or just make the indexes wrap around. That's probably the best solution, right? Just perform a modulus operation on whatever the pointer output is. So why do we use multiple pointer data pairs? Allow me to explain. It reduces the chances that an attacker can get away with stealing just part of our array, right? So every time he performs a new decryption, he gets a new pointer that points to somewhere else inside of the array. It's like over here, and then the next time he tries a new password, it's over here, and he's got to chase it, right? Well, maybe he gets lucky. Maybe he gets super lucky, or maybe you have tons and tons and tons of passwords. Say you have 100,000 passwords or something. Well, then certainly if he decides to steal like a 10th of your array, and maybe he can do that depending on how big you make it. Maybe a 10th isn't too large, right? He takes that 10th back with him. Maybe he gets all of your hashes. The assumption would be that if you're using a randomly distributed pointer system, that for the proper decryptions, a 10th of all of your passwords for your service are going to be inside of that 10th of the array, right? So he has a chance to crack some of them. The more pointer data pairs that we use, it quickly compounds. It becomes exceedingly unlikely that he will be able to steal just one little portion of the array and get away with it, right? So that's why we use more, right? Because then he doesn't have just one, they're all over the place. And as soon as you have enough of them, then it becomes statistically impossible, right? So, also, yes, this is why we hash the data. Don't just be like, hey, we can just store the data inside the ciphertext, right? That saves one hashing. Hash the data, because if you don't, he's only going to need one pointer data pair to be able to say whether this is a true or false, right? For example, if he has a bunch of them, he steals a very small portion of the array, right? He has a bunch of pointer data pairs inside of the ciphertext. He just goes through the pointers until he finds one that's inside of his area, and the more pointer data pairs that we have at this point, the more likely it is that he'll have one inside of the small portion he's stolen, right? And he just says, oh, hey, is that true or false? And because we chose a data length that reduces the likelihood of collisions, then it would be highly probable that if there is a true or false there, that is the answer to the question, right? So that's why we hash it. Get back up here. So he can't, yeah, sure. So why would the attacker not just steal the pointer data pairs from the file, right? So he's going to. The pointer data pairs are stored as a ciphertext. He's gonna steal them. That's the assumption, because that ciphertext is replacing our hashes, and we're still assuming that it's very, very possible for him to steal the hashes, right? They're stored as a ciphertext, which means they're stored in a format that he has to have a key to unlock them back out. If he types in the right key, he'll get the right pointer data pairs. Makes sense? But if he types in a wrong key, he'll get something else, right? We're making it so that our pointer data pairs are indistinguishable from the true random output of a failed decryption. So therefore, every single decryption is going to give the attacker a different set of pointer data pairs, not the same set. So he won't be able to steal them. So does that make sense? Is that a good answer? Anybody? Okay. Yeah, you guys can ask me questions if you want, but Tim, you're up. Asia.
Thanks, Dave, for this. This was delightfully disgusting. So let's talk about this as a reality, okay? You have a password. The password is 1234. Let's see how that stacks up against a couple different types of attacks given the introduction of ball and chain. So online attacks. If you're conducting the proper anti-automation mitigations, right, and you're doing the proper monitoring and defense on your network, online attacks almost should not be able to happen against a password like 1234, right? Because one, in true brute force attack, how many tries does it take to get to 1234? Quite a bit, right? Quite a bit. The second thing is who has a 4-character password in their word list? Raise your hand if you have a 4-character password in your word list. Not a whole lot of you, because who has a 4-character password anymore, right? Except for Tim Madden. He's got a 4-character password, okay? So online attacks, I mean, even given like the current implementations, online attacks should be null and void, right? We should not allow online attacks against our passwords. It's too easy to do with the technology that we currently have. And then if we're able to prevent offline attacks against our passwords as well, then a password like 1234 becomes a secure password. Not a strong password, but a secure password. And that's pretty ridiculous, isn't it? I mean, that's pretty awesome. Right? So we understand, like, ball and chain's complex. I mean, with the stuff he just talked about, the reason why he's talking about it, and I'm not up here doing anything, is because I don't get it, right? That thing is it's above my head. I'm not embarrassed to say that I'm not a crypto guy. I don't understand crypto. That's why there's people like him and some of you that do that stuff, and I don't. All right? So it's complex, and we understand that, but our objective isn't necessarily for everyone in the world to implement ball and chain today. Okay? That's not our objective. It's about pushing the industry forward. Okay, so market research shows that if you give a consumer a choice between something that's expensive but very capable, cheap and not so capable, and then something in between, they typically choose the something in between because they get this perception that it's the best of both worlds. And in economics, they call this the Goldilocks principle. Okay, so let's look at our current implementation trend. All right, adaptive hashing, it's seen as too complex, too costly. Plain text and encoding is finally, at least from my experience, begin to be seen as too insecure. I don't see too many passwords being stored in clear text anymore, okay? And fast hashing seems to be just right. So if you look at the graphic right here, I went and I took a bunch of statistical data out of the Pwn list leaks database, and for the leaks that report what type of hashing algorithm was used, how many of those there are using adaptive hashing functions? 2 instances. The rest of them, 1,300, are all using fast hashing algorithms. So the evidence right here from Pwn list supports the current trend. Wouldn't it be awesome if we could do something like this? What if the projected trend was now that something like ball and chain or a similar implementation becomes too complex but too costly? And then fast hashing now becomes too insecure. But then adaptive hashing becomes the just right implementation. Well, we've pushed the industry forward. This is still a win, okay? This is still a win, but we do need to change the trajectory. Because if we keep going down this line of creating more complex and slower hashing algorithms, all we're doing is kicking this can of computational warfare against the attacker down the road. And that's a war that we're not going to win. Okay? So BAC and things like it are a real solution and a step in the right direction. We need to focus on trying to identify the advantages of the defensive perspective. Right? In ball and chain's case, it's the fact that we can create these huge, massive things, right, and we can prevent them going through our small pipe to our network. That's something that we control. Okay? So in closing for the talk, it's not really a matter of if, it's a matter of when you're going to get breached. So anytime you're designing a password or a credential storage security system, right, or you're implementing a new one, designing a new one, just keep in mind that you need to assume the eventual compromise of that system and do your best to protect those credentials. Now, as far as the goods go for this particular talk and the things that we talked about here, here shortly, probably in the next 24 hours, this Bitbucket repository will become available. That's got some of the very early proof of concept code that we've put, or that Ben's put together for this. This isn't just like a Ben-only project. You know, he wants your help. I want your help. Let's get a community of bright minds, and we have the brightest minds here at DerbyCon, do we not? Yeah, all right. Yeah, holler if you got a bright mind. I want to hear everybody else. All right. We want you guys to help, guys and gals included. We want you to help us perfect this, help us design this, help us come up with new solutions to change this trajectory of the way we're going. All right. Reddit Ben's pretty active on Reddit for a discussion about OpenBAC here. Follow him on Twitter for the latest stuff, for the latest information about it, and also for an announcement for when he finally releases the full technical white paper if you're interested in all the excruciating details. And of course, feel free to follow either of us on Twitter if you want just security-related stuff. So with that, I'd like to open up the floor for some more questions, and myself and Ben will do our best to answer them. Go ahead, Tim.
How do you make sure the data doesn't point outside the data set? You could exclude passwords if they point outside the data set.
So you're talking about the pointers that point outside the thing, like what I was talking about with the 0, 1, 2, 3, right? How do we make sure? So I can go back to the slide if you want. We have a couple solutions that I've dreamed up. Oh, damn it. Okay, yes. How do I make sure that the pointers do not point outside of the data set? Okay, so the solutions that I had for that were... Did I miss them? Here we go. This one. Ha! Cool. Do you want me to explain them? Or? Okay, cool. So you can just ignore it, because if the pointers point outside the data set, all the attacker knows is that that is not the password. He just knows, okay, so that points outside the data set, therefore they could never confirm or deny if that was right, therefore it's not the password, right? Cool? So you can ignore it because it's never going to be the password. It's always going to be something that's not the password. Now, if the attacker knows, the assumption is that the attacker knows it, because we're not going to do security through obscurity, right? We're going to assume that he knows everything about our operating, the way that we're operating, just that he just can't do what we're doing. We're going to beat him in math, not in obscurity, right? So, well, yeah, here's the thing, is that there's other solutions to it, right? If you don't want to do that, it'll never give him the password, but you can also just match the pointer space. So you can match it perfectly. You can say, here, this box is all my pointers. Let's just make sure the array fills that box, right? You can make sure they're the same size. That's going to limit the amount of arrays that you can have, especially as we start getting into higher order numbers. That's going to become a little bit ugly, right? But it works out. You can use non-sequential indexes, which is what I was talking about, where we would make it so that they're not his decryptions. The pointers that he gets are not sequential, right? And you can just map. So forget about how you map it. Just let's say the pointers are random, and the random pointers somehow point to some ordered location inside of the array, right? And we make sure, therefore, that there is no maximum size. He doesn't know what the maximum size is. He loses. The issue with that is just simply that you have to actually find a way to map those out, right? Or you can just make them wrap around. Making them wrap around is probably the best solution. I'm not sure yet. I want to do a bunch of math on that and make sure it's the best solution. But you just say, okay, here's my pointer space, and my array fills up half of it, right? Well, that means 50% of the time a pointer is going to point somewhere else. Okay, let's just modulo, just flip it over, right? You guys know modulo, right? Okay.
Sure, some of us do.
Yes, sir. How do I handle data set rotation?
So in the attack.
Yeah. Definitely. So denial of service is possible with this system, as you would assume it was with any sort of, I mentioned network accessible storage. So how would I handle if the attacker stole my seed or something like that, and then was somehow able to determine it, and just how would I handle it if the attacker found any way to get my array, right? Obviously, you're going to immediately change all your passwords. You just create a new array. You say, everybody change your passwords, right? And that's kind of a pain in the butt, but you can do it. We can just create it again from scratch. I do want to point out with that the protections of ball and chain does not just stop simply when the attacker gets it. Remember, guys, there was a slide a little while back where we talked about how it's such a pain in the butt for the attacker to work with it as well, right? So even if he does somehow manage to steal it, it's still a huge problem for him. It's a ball and chain, and he's trying to drag it around with his leg, right? But yeah, just cycle it. Yes. Would be the assumption. Yeah, we would assume that the pointers are chosen at random for every different person, for every single person, for every single account. Yeah, if we use the same pointers, that would be a problem, right? Because eventually he's going to figure something out. He's going to crack one or two passwords maybe. The assumption is he never does, but maybe he does, and he starts to figure out, it's like, that's weird. Maybe he makes an account, right? So, yes, sorry. Yeah. So have I seen how scalable it is in terms of performance? How quickly you could run this algorithm? Of course, that's going to depend entirely on the specific implementation that you or we as a community decide on, right? But I was looking into it a little bit. It looks like it's probably going to be about 3 or 4 times slower. It depends. But I would say, in comparison to what we're doing, like we're talking, even if it's 3 or 4 times slower, that's not that big of a deal. Like, we're already talking about like adaptive hashing algorithms that want to go like 500 rounds or something. Like, it's going to be faster than that. Yes.
I don't understand a lot of these things.
Sorry.
I feel that this is a great idea, but not pulling this big heavyweight with you. I would assume when you have all of this array, you will have some kind of an API. So that an attacker
Yes.
goes inside your system, why you wouldn't use that API to encode it, to decode your password instead of trying to take the whole file away?
Sure, yeah. So so the assumption is that the attacker could maybe piggyback on our legitimate authentication channels. We're going to have some sort of channel or API or something through which we make requests to this gigantic array. And the assumption is if the attacker owns our client system, he might, or owns some endpoint to that API, he may be able to piggyback on that and make requests to it, right? In that situation, if the attacker already owns one of the endpoints, owns one of the systems on which, we're making we're actually performing the authentication, which would be the only ones I would hope you guys would expose to the API, the attacker is already going to be able to run some sort of attack like Mimikatz. So you're right in that he could do that, and we can stop that in terms of like man-in-the-middle attacks and stuff. We can block him out from doing that, right? But if he already owns an endpoint, he'll run Mimikatz, he'll put a keylogger on it, he'll just do something there, right? He'll dump the passwords from memory as you perform them, he'll replace the binary. So that problem isn't as big of a deal, right? Does that make sense? Correct. And the hope is that that would be easy to stop, however, right? Because offline attacks are very, very easy to identify and stop. Do you want to say anything?
So there's 2 very different types of online attacks, right? There's the online attack against the web interface itself from any third-party location, right? From you sitting in this room right now on your laptop. We can prevent that now with our current technologies, and we should be doing so. I'm not going to say that everyone is, because every day I find somebody that's not, right? But they should be doing that, and we can do that very easily. The other type of online attack is, they've compromised the actual server that conducts authentication. The only endpoint that's allowed to query the API that checks this actual blob of data, right? Well, if he owns that server, then he's already got keys to the kingdom, right? If he owns that particular server, there's other things he can do to get that information much easier than actually querying the blob of data. So security is what? We hear it all the time. It's a layered approach. This is one layer that goes along with preventing offline credential cracking, but we still have to protect our systems, right? We still have to protect our networks and do our due diligence to protect everything around us through our perimeter. So, any other questions? Got just a few more minutes. Lynn.
I'm looking into that, and I'm super, super, super excited about it. I'm not sure yet. The question was, because I'm terrible at that, sorry guys, was could this be used to potentially store other types of data, like credit card data, right, and keep that from being extracted from the network? Maybe.
Maybe. The answer everyone loves to hear.
Yes, sir. Right there. I'm looking at you. Yeah, so like I said, somebody could purposefully corrupt the file, right? That is possible. Denial of service against this system is very, very possible. If you run it over a wireless network, somebody could perform a deauth attack and turn the wireless network off, right? So deauthentication, denial of service against this system, because it is, there are calls, there are things going on, there are things we need to keep, that creates a problem. It would be very, very hard for somebody to potentially do that, would be the hope, and that never, ever reveals the passwords as far as I'm aware. So, we're almost out of time. I do have business cards if you guys want, so you guys can contact me. I'm open for any and all questions you have. I really, really hope that you guys would like this idea, get engaged with me, and let's make this a reality. Thank you so much for coming, all of you.